Hi everyone, I hope this video finds you well. We're going to be continuing on with our discussion of section 2.2 from your textbook, discussing a little bit about matrix multiplication as a follow-up to talking about matrix addition, subtraction, and scalar multiplication. Now, your book builds matrix multiplication up sort of from the ground, basing it off of an extension of the dot product. If you want to see a full discussion of that, I would recommend reading through that part of your textbook. But for us, we're going to jump right into a definition for matrix multiplication and then look at some examples of matrix multiplication as well as some of its properties. So for matrix multiplication, we're going to go ahead and we're going to let A be m by n and b be n by p. So you'll notice that there's sort of a size requirement for matrix multiplication to make sense. We're going to require that the number of columns in the first matrix matches the number of rows in the second matrix. Then the product AB will be m by p and have elements. Well, we'll say that AB has, in its ijth element, it'll be the sum from k equals 1 to n, where k is just an index and n is that shared number of columns for A or number of rows for B. And you will do that as you go through AIK and BKJ, multiplying those values. Now this multiplication here is actually just a normal multiplication because AIK and BKJ are just values, so that's just a normal multiplication of numbers. What you should sort of see from this definition is that this piece here runs through the ith row of A, whereas this part here runs through the jth column of B. So what you're basically doing is you're sort of doing an extension of the dot product. You're taking the ith row of A and doing a dot product with the jth column of B. And that dot product, which results in a single value, gives you the ijth element of the product. So you guys can sort of think about how this is an extension of dot product. And of course, like I said, in your textbook, they do a much more thorough sort of buildup of why that definition is the one that we want to use. For us, though, we're going to go ahead and jump right into looking at some examples of this. So let's take a look at a couple matrix multiplications. So to do that, we're going to define a couple matrices. So let's have A be the matrix 5, 4, 6, 8, negative 1, 2. And we'll just make a note here that A is a 3 by 2 matrix. Then we're going to have B be sort of a 6, negative 1, 1, 3, and then 2, 0, 2, 4. So B here, of course, would be a 2 by 4 matrix. We'll define another matrix, C. We'll make this guy a square matrix, 2, 0, negative 1, 5. This is a square 2 by 2 matrix. And then D will also be a square matrix. We'll also make this guy 2 by 2, negative 3, 4, 1, 1. And this guy's also 2 by 2. So let's try to evaluate, if possible, right? I don't know, let's try AB, AC, CA, CD, and DC. So we'll try those 5 matrix multiplications. So let's start with AB. First of all, let's think about whether or not AB is going to make sense. This is going to be a 3 by 2 with a 2 by 4. So you'll notice that these two values, right, that number of sort of columns in the first matrix and the number of rows in the second matrix do match, so the multiplication is going to make sense. We also expect that the result, what we get from A times B, is ultimately going to be a 3 by 4 matrix. So in other words, we expect our answer for A times B to be a 3 by 4 matrix. Let's go ahead and see how we would calculate that A times B. What we're going to do is we're going to go and take each row, going this row, then this one, and multiply it with each column of B. So that first element what we're going to do is we're going to take the first row of A and multiply it with the first column of B. And when we say multiply, we really mean do that dot product. So when we do that, we would get that 5 times 6 plus 4 times 2. Now 5 times 6 is going to give us 30, 4 times 2 is going to give us 8, and our first element should be 38. Then we can move along staying in the same row but change columns. So we'll take the first row of A, and now we'll do the dot product with the second column of B. When we do that, we should get a negative 5 and a 0, and then that negative 5 plus 0 is going to give us negative 5. Then we will continue staying in the first row, but now moving to the third column, doing that dot product. Then if we do that, we should get a 5 and an 8. Adding those together, we get 13. And then finally, we will take that first row times that last column. Doing the dot product there, we should get a 15 and a 16. Adding those together, we should get 31. All right, now we'll move into the second row, and we'll go with that first column. Again, doing the dot product there. 6 and 6 will give us 36, 8 and 2 will give us 16, 36 and 16 added together, sounds like we should get 52 there. Now we'll move a little bit faster, because hopefully the idea is sort of becoming clear. Next one we should get is negative 6, then we should get 6 plus 16, which is going to give us 22, and then we should get 18 plus 32, which is going to give us 50. Finally, we'll now move into the third row and each of the 4 columns again. So doing the dot products here, we should get a negative 6 and 4, so that sounds like a negative 2. Then we should get a positive 1 and 0, so adding those up will give us 1. Then a negative 1 and 4, which should give us 3. And then a negative 3 and 8, which should give us 5. And notice, as predicted, this big matrix here is indeed a 3 by 4 matrix, as we thought it would be. Okay, now that was a lot of computation. We'll do the other ones a little bit faster just to see if we get a hang of this. So let's think about AC. Is AC going to be sort of well defined? Well, A, since we just worked with it, we know that that's 3 by 2, and C is 2 by 2. So this is going to sort of work as those two things match. The overall result is going to come out as a 3 by 2 matrix. So let's see what 3 by 2 matrix we actually get here. All right, to start with, we'll take the first row of A and use the first column of C. So if we do that, we're doing the dot product of 5, 4, and 2, negative 1. That sounds like we'll get a 10 and a negative 4, so that should be a 6. Then 5, 4, and 0, 5. That sounds like we should get 20. 6, 8, and 2, negative 1. Sounds like we should get a 12 and a negative 8, so a 4. 6, 8, and 0, 5 should give us a 40. Negative 1, 2, and 2, negative 1 should give us a negative 4. And then negative 1, 2, and 0, 5 should give us a 10. So there's the matrix AC there. Notice, as sort of predicted, this is indeed a 3 by 2 matrix. This guy right here is indeed 3 by 2. Okay, now for the first sort of moment that's not going to be just purely computational here. What happens if we change the order of the multiplication? So what happens if we consider ourselves talking about CA? Well, is CA well defined? Well, C was 2 by 2 and A is 3 by 2. You'll notice that this time, these values here don't match. In other words, right, this is not well defined. So we actually can't perform this multiplication. If you imagine trying to do that multiplication, what would you do? Well, you take the first row of C and you try to multiply it or do the dot product with that first column of A. But this guy would only have 2 values, and this would have 3. That dot product isn't going to make any sense. That's why this guy's not well defined. Now you can see that that's a big deal, because that means that the order of the multiplication impacted the result. Here, when we did AC, we actually got a natural result. CA, though, is not well defined. So the order of the multiplication makes a big deal. Okay, let's go take a look at these last ones involving the square matrices. So CD. Shouldn't be any doubt that this guy's going to make sense, right? This guy's 2 by 2. This guy's 2 by 2. Everything seems to be based on 2 here. So, of course, these two are going to be together. And that's going to make sense. And then the overall result should come out as a 2 by 2 as well. Notice that this is also sort of telling you why square matrices are so nice, because when you work with them, you know, if you multiply them together, we know that they're going to preserve the sort of size. 2 by 2s with 2 by 2s are going to remain 2 by 2. All right, so we're going to start by taking the first row of C with the first column of D, doing that dot product there. Looks like we should get a -6 and a 0, so we should get -6 there. Then first column and second row should give us an 8. Then second row and first column looks like it should give us a 3 and a 5, which is also an 8. And then so that second row with the second column looks like a -4 and a 5, which should give us a 1 overall. So our matrix there should be -6, 8, 8, 1. Okay? Notice, interestingly enough, CD is a symmetric matrix in this case, even though both C and D individually definitely had nothing to do with sort of symmetry. All right, let's do one last one and change the order of the multiplication here. Now, if we change the order of multiplication and talk about DC, well, the size isn't going to be a concern. Since everything's 2 by 2, these two are going to match, and the result is going to be still a 2 by 2. Is it going to be the same 2 by 2 though? Well, let's see. So we'll start by taking the first row of D with the first column of C. When we do that dot product there, it looks like we should get a -6 and a -4, so we get a -10. Now immediately, if we're just interested in whether or not these two things are going to be the same, we already have our answer. Remember that for two matrices to be the same, they have to have the same element in every position. So the fact that we got a -6 there and a -10 there already tells us CD is not going to equal DC. But let's get the rest of the values. We'll take the first row of D with the second column of C, and that should give us a result of 20. Then we'll take the second row of D with the first column of C. That should give us a 2 and a -1, which is going to be 1. And then finally, the second row of D with the second column of C. That should give us a result of 5. So we will notice here that this is sort of a big comment that we want to make here. We should note matrix multiplication is not commutative. And this separates it from normal multiplication. When you guys are multiplying numbers, 2 times 3 is the same as 3 times 2. But unfortunately with matrices, C times D is not necessarily D times C. There are matrices out there that do commute under matrix multiplication. In other words, there are some matrices A and B where A times B is the same as B times A. But as a general rule, matrix multiplication is not commutative. It is not commutative. So you cannot make that assumption that A times B is equal to B times A. That means the order in which you write a multiplication for matrices is very, very important. Sometimes, if you change the order, you'll end up with something that is not well defined like we saw here. And even if it is well defined, the order of the multiplication might give you different results. So we know matrix multiplication is non-commutative. What sort of properties does it have? In other words, what properties do apply to matrix multiplication? Well, we'll talk about that on our next page here. So let's talk about a couple properties that are true for matrix multiplication. The first one is that it is associative, meaning that if you have 3 matrices that all have the appropriate sizes for the multiplication to make sense, then if you do A times B times C, so you choose to multiply B and C first and then multiply A on the left to that result, that's the same as first doing A times B and then multiplying by C. So that's what it means to be associative, and that is true for matrices under multiplication. The second one is that it is distributive over matrix addition, and that means if you have a matrix A and you multiply it over a sum B plus C, again assuming that all the sizes make sense here, that's the same as doing A times B and then adding that to A times C. You'll notice though that we are being very careful and placing this A on the sort of left-hand side of B and C. And that is important. It would not be correct to write that A times B plus C is the same as BA plus CA, right? The order here is very important because we just learned that matrix multiplication is non-commutative. Well, that means we actually need another distributive property. If you multiply on the other side, you get the same result. So if you have A plus B, and then you multiply by C, that's the same as AC plus BC. Notice again, though, we are being very careful about having this guy come in on that right-hand side here so that C shows up on the appropriate side of the multiplication. Now, this is proved in your textbook, and it's good proof to look over because Proving things by elements in matrices is something that we will be doing, and you guys will be seeing some proofs like that, so it's good practice to take a look at that. We're going to prove this one right now, and then as an exercise, I would sort of look over what we do for property 1, read over what your textbook does for property 3, and try to write up your own proof for property 2. Property 2 should have a very similar proof to property 3 since they're pretty much the same property. But we're going to go ahead and prove maybe the messiest one, which is talking about associativity. So we'll do that on sort of the next page. So we're going to try to prove the associative property. So we're going to be a little careful here. We're going to let A be m by n, B be n by p, and C be p by q. So all these matrices have different sizes, but you'll notice that the multiplications will make sense because if we multiply A and B, these values will match. And if we multiply B and C, these values will match. So all the sizes are chosen so that the matrix multiplication is appropriate. What we need to show, right, is we need to show that A times B times C is the same as doing A times B and then multiplying by C. To do this, we're not going to show this in overall for the matrix. We're going to show this by the elements. So we really need to show that the ij element of that guy is going to be the same as the ijth element of that, because that's what it means for matrices to be equal. They have all the same elements in the same positions. We're not concerned about size here again because we've already made the assumption that the sizes will work out. Okay, so let's go ahead and see the proof of this. So we're going to start from this sort of left-hand side here, and we're just going to work our way as a direct proof over to the right-hand side. So let's start by taking a look at what we can say about the elements of this guy. Okay. Well, this is a multiplication. It's a multiplication of A and the elements of this guy. So let's use the definition of matrix multiplication. We can say that this is the sum from k equals 1 to n. How do we know to n? Well, we know that A is m by n here, and we know that that BC will technically be n by q. So the shared sort of index here is going to be that n with that n by q. So it is going to run through n here. So we know then that since we're talking about that ijth element, it'll be aik. And then we'd have to talk about the kjth element of that multiplication, b times c. So this is our sort of standard definition of matrix multiplication. The only thing that's a little bit different is that that kj applies to this product b times c. But we can break that down even further. So let's use the definition of matrix multiplication again to break down that second component. So we'll keep our aik here, and we'll try to use the definition here. Now, b times c, if we think about that, is going to be about these sizes here. So the shared index is going to be that p. So we can write this as another summation. We'll use a different index, L equals 1, and it'll run to p this time. And that, well, we'll want the kth sort of row of B and the jth column of C. So that'll be BKL and CLJ. So that right there gives us the breakdown for this matrix multiplication. And this entire expression gives us the breakdown for this sort of triple multiplication. Now, this is a pretty sort of nasty expression, but you got to remember that all these things in here, this, and this, are just numbers now. They're not matrices, they're elements of these matrices. So they're just numbers. This, of course, is a sum, and we know that numbers distribute, multiplication of numbers distribute over addition. So we're going to distribute this guy through that summation. So let's see what that would look like. That would give us the sum from k equals 1 to n, and then the sum from L equals 1 to P, and then we'd have AIK, BKL, CLJ. All right. Now, we're not maybe super comfortable with summation notation, but again, do remember that summations are just adding numbers up. So it shouldn't matter the order in which we do those additions. So let's switch the order of the summations. Let's think about this as the sum from L equals 1 to P, the sum from K equals 1 to N, and then AIK, BKL, CLJ. Okay, but let's look at this here now. Well, this, if you think about this, this is running from on index K, which this has a K and this has a K, but this guy does not. So this is all we really need to consider right here. This, of course, is the definition of matrix multiplication. It's telling us about the ith row and the lth column of A times B. So let's write that. We can say that this is the sum from L equals 1 to P, and we can talk about how this is actually the IL element from that AB, of course, times CLJ. So all we're doing here is we're saying that this entire expression here is equivalent to that IL element of AB. But now notice that this, right, is talking about the ith row of that and the jth column of C. So we can use the definition of matrix multiplication one more time to talk about how this is actually the ijth element of AB times C. Well, if we go all the way back up to what we were trying to show, right, we wanted to show that the ijth element of A times BC is the same as the ijth element of AB times C. And that's exactly what we've done. So we completed our proof. We slap a little QED on there, and we're all good. So that's a quick proof of the associative property. Pretty messy because of the sort of double summations and everything. This should tell you that in the long run, we don't really want to have to prove things by the element definition of matrices, but that's what we have thus far. It's a little messy to do so, but we were able to prove this property. We're going to wrap this up by just talking a little bit about some other notation and one very sort of special matrix. So when we're talking about square matrices, we saw that when you're multiplying square matrices, provided their square matrices are the same size, we're not too concerned about the size limitations because they have the same number of rows as columns. So sometimes you guys will see sort of power notation for square matrices. So we should just keep in mind, let A be n by n. Then, as with standard numbers, we define something like A squared actually means A times A. Something like A cubed is actually A times A times A. And something like A to the n is actually A times A times A, where those multiplications are repeated n times. So just so you guys know, whenever you have a square matrix n by n, you can continue to use multiplicative notation, but if you see that power notation, it acts just the same as power notation for numbers. Obviously, this is right now only well-defined for positive whole number exponents, 1, 2, 3, 4, etc. There are some extensions about talking about how to raise matrices to other exponents, but for right now, just keep in mind it is positive whole number exponents. All right. Very, very sort of important matrix that we're going to introduce is what's called the identity matrix. So the identity matrix is an n by n matrix written I sub n with elements I sub n, ij equals 0, I not equal to j, and I sub n, ij equal to 1 if I equals j. So the identity matrix is always a square matrix. So there's an identity matrix of size 1 by 1, which is of course just the number 1, 2 by 2, 3 by 3, 4 by 4, etc. We don't really have a formal identity matrix for non-square matrices, so it's always just going to be a square matrix. And the identity matrix's elements are very simple. You have all zeros everywhere off the diagonal, and you have ones on the diagonal. So just make sure we're clear with that. Something like I2 would just be 1, 0, 0, 1. And something like I3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's what the identity matrix is. Now, I gave sort of a direct definition of this. In your book, they use what's called a Kronecker delta notation. You don't really need that notation as long as you're comfortable with this definition that we gave. But it is also an appropriate way of defining the identity matrix. Why do we care about the identity matrix? Well, the identity matrix is sort of the matrix we use to sub in from multiplication by 1. We know that in normal multiplication, like if you take 5 times 1 or 1 times 5, you always get back to where you started, right? The number 1 is a unit for multiplication. Well, the identity matrix serves the same purpose. So let's talk about two important properties of the identity matrix. So we're going to let A be m by n, right? So two properties here. If you take A and you multiply it by the identity matrix of size m by n, then, let's go back and just quickly erase that. If we multiply by the matrix in, then you'll notice that this guy here will be m by n, this guy will be n by n, and the multiplication will actually give you just back your original matrix A, which will actually continue to be m by n, of course. And second, if you do im times A, so this is an m by m matrix, and this guy is m by n, then the result will also be A, which will of course be m by n. So this sort of shows us that the identity matrix acts like the number 1 under matrix multiplication. The only thing that you should be aware of, though, is that if A is not square, if A is m by n, you'll need a different identity matrix. You'll need the n by n here, where you'll need the m by m matrix there. So your book proves one of these as well and leaves the other one as a proof to you guys. I'd recommend reading through the proof of this guy. So this is proved in textbook, and you should try prove this yourself as an exercise. And again, what you'll want to do is you'll want to do a bi-element proof, just like we did for the associative property. We'll be finishing up section 2.2 in the next video, talking about some properties of the transpose, how the transpose works under matrix multiplication, and then we'll be moving on to why we want all of this stuff about matrices.